Okay, cool. So I think I have everything set up now. Cool. Yeah, so as usual, we're going to have the regular sequence of events with our Canvas attendance quiz with the quiz passcode in the bottom corner and in the chat. We'll have pre-lab Zoom feedback, and then we're going to go through the answers to the Canvas quiz from last week because we got quite a few questions about what the answers to that was. And then we have both lab content on slides, kind of going through tensor products and the material covered in lecture this week again, and then also running the same computations using the IBM Quantum Experience platform. So this week's question is, if you read the weekly announcements posted on Canvas, if it's not a great, like if it's not the platform you check most often, you could maybe change like how we do it to make sure we reach as many people as possible. But since you are submitting all of your problem sets on Canvas, I hope you do log in every once in a while. Yeah, so we also have our pre-lab Zoom feedback, which I'll start up right now. This material was this week's material was on multi-qubit states and tensor products, which is how you go from a single qubit state to a 2 or 3 or n-qubit state. It's a little bit more mathematically challenging, I guess, than some of the material we've had in recent weeks. So I know like it may require a little bit more review, which is why we're trying to do that today. And also we want to go through how this translates directly to what you get in the quantum experience simulator. Cool. So I'll let that run for a second and I'll go through the Canvas quiz from last week. So we had 4 questions on the Canvas quiz last week, kind of going over your understanding of the quantum mechanics content we covered earlier this semester. So the first statement was that if quantum states can be represented by vectors, and the direction of those vectors gives us information about the probabilities of different measurement results. I guess I don't know how to write that or how to say that in simpler terms, but the idea is if we have our block sphere, the vector that we would write on the block sphere to represent a certain quantum state, like maybe this, could tell us that we have primarily, like let's say 0.8 square root of 0.8 times the 0 state plus square root of 0.2 times the 1 state. And then we could also have a relative phase between these 2 states. So, and that affects where we are along the equator for this vector. So this is true. You can kind of visualize it on the block sphere. Actually the relative phase of the 2 states does not impact our measure, or yeah, the relative phase of the 2 states does not impact our measurement. So our measurement probabilities, if we instead had this state, I'm sorry, I wrote a really ugly one up here. It looks kind of like a phi. If we instead had this state, these both have the same probabilities, because our probabilities, like our P of being in the 0 state is equal to, I guess we often call it alpha squared, the absolute value of alpha squared, which is equal to the absolute value of square root of, I've written this a little bit ugly. Now I'm in black. Okay, here we are. 0.8 squared, which is equal to the absolute value of negative 0.8 squared, which is of course just 0.8. So the relative phase of our two states actually does not impact our measurement probabilities, but the direction of the vector in the, I guess, zx plane or the zy plane, depending on how you want to look at it, does tell us what our relative probabilities of our measurements are. So if you answered false to this, you may have been confused about the two planes that we can describe our quantum state in, because there is, the xy plane does not give us any, or like the position in the xy plane does not result in any change in our measurement probabilities. It's only the change, it's only the xz plane that affects it. The second question was, if when a quantum state is measured, it can change as a result of the measurement. And that is true. There are many different ways and reasons that this can occur. One is just that whenever we perform a measurement, we do have to interact with our system in some way. And so if we interact strongly with our system, then we will like functionally be entangling our measurement device with our quantum state. And so that will change the quantum state. This like interaction can also result in dissipation through the measurement device, like as a loss channel. So if you think of it like you want to measure the temperature of your refrigerator, and your refrigerator is closed, so it's all sealed, it's at a certain temperature, but then you open it to put the thermometer in. You've opened it to air and it's probably warmed up a little bit, maybe not substantially, but it could be like a degree or two, depending on how long you have it open. So that's kind of the idea of dissipation. You now are losing some of your information into the general environment. The third statement was that quantum states always stay the same and they never change. This is false. Hopefully, because we are working on quantum computation, we're applying gates to our quantum states. You are pretty familiar at this point that we can manipulate our quantum states pretty selectively and pretty well at this point. That's the whole kind of foundation the field is built on. And if we couldn't do that, if the quantum states always stayed the same, then that would not be able to happen. And then the final statement that quantum states can be represented by a single number, a scalar, and the measurement of the state gives us that number as a result. This is false. So if you were, so the real, I think this is kind of a confusingly phrased question personally, but I can tell you where you might have gone wrong if you got this wrong. Of course, this was graded, but only for the purposes of us evaluating how well we're teaching you guys. It doesn't affect your grade, it affects our grade. So the statement a quantum state typically refers to often refers to the wave vector of the quantum state. So the actual quantum state we're looking at when we put it on the Bloch sphere is some psi. When we perform a measurement, though, we can only measure an observable, like the energy of the quantum state. And so those energies can be represented, like those energies are a single number, they are a scalar. There's not a vector energy that we're like computing or measuring. And measurement of the state will give us that energy eigenvalue that is related to the state. So I think like it's a bit confusing because if the way you could know for sure that the answer you wanted is false is if we have a quantum state that is a superposition of two states. We have two possible energy eigenvalues we're going to get. Our energy could be 0 or 1, like whatever energy that corresponds to, each with 50% probability. So in this case, this quantum state cannot be represented by a single number because it has a probability to be in either of these two numbers. And that probability is defined by the wave function of the state, not the observable value that we're actually measuring. Does all of that make sense to you guys? Or are there any questions about this overview or any kind of like starter questions for this week's material? I can also answer them as we go along. So just post if anything occurs to you. Okay, I'm not seeing anything. So hopefully we are getting everything that you guys, or everything makes sense so far. Okay. So the learning objectives for Lab 17 are trying to demystify and review tensor products by taking them by hand and then going to using NumPy to calculate these tensor products, which we will be doing through the IBM Quantum Experience, just because it has a nice built-in Jupyter Notebook platform that allows us to use Python pretty easily. And then we're going to actually use the QASM simulator to create a Bell state and then run that circuit. And then at the end, if we have time, and I guess I'll stay late to go through this because this is a recorded section, I'm going to go through using the Circuit Composer widget that allows you to drag and drop the quantum gates that you want. Like you run like a line of Python code, and it will open up an interactive little cell in your Jupyter notebook, and you can drag and drop circuit components just like you do in the quantum experience that's not coded in Python. And then you can then export the circuit that you've created into a bunch of Python code and Qiskit. So it'll do it for you automatically. You don't actually have to program it yourself. So that's pretty useful. So the first topic for today is writing multi-qubit states. These states are used in almost all the quantum circuits that are of interest to us because you need to have more than one qubit to demonstrate entanglement, and you need to have entanglement to demonstrate teleportation. And a lot of these algorithms also rely on beginning in some kind of entangled state. So last week, we did see some examples of these 2-qubit states, but we didn't really go into how these states work or how you can calculate or define them. So if we have a 2-qubit state, because there are 4 possible, like there are 2 possible values for our state vector for each qubit, and so we multiply the number of qubits times the number of possible values per qubit, and we get 4. We can write them out with this 0, 0, 0, 1, 1, 0, and 1, 1 state. So that's great that we can write them in this kind of broad ket form that's pretty, like, I guess, intuitively nice picture, but it doesn't actually tell us what the vector values for these kets are. So if we want to move these states into our ket form, then or if we want, we can write these states in a ket form for a more complex psi value by just having the relative, like relevant amplitudes for each of these states, and then writing it out in a vector form. But now we want to generalize this to any quantum state that we might want to create. If we know what state our qubit 0 is in, we know what state our qubit 1 is in, what is our combined 2-qubit state. So the way we do that is using tensor products. And to kind of give a less quantum analogy, we're going to use Phil and Aman, who are 2 of the other TAs, and they're going to go to dinner at an Italian restaurant, and they're going to order one of the 2 meals available, which is pasta or pizza. This is Phil, this is Aman, and they can choose one of these 2 dishes, but these are the only 2 dishes available for now. And so we want to kind of, I guess, we could draw a graph for what's available for each of them. So you'd say that Phil wants pasta, or Aman wants pasta, or Aman wants pizza, or Phil wants pizza. So you can see we have 4 lines drawing it across, and all these combinations can be written out with each TA choosing one of the 2 options. And you might want to note that the ordering is important in these. Generally, we do consider our qubits to be identical particles. So we can have our qubits in either order, or like I guess like the ordering does matter, but they can have either state. They're not like restricted to like one or the other. But it is important to note that we're never going to swap our qubit states in like a notation sense. Like the first qubit, like if we're writing out our qubit state, it will always be qubit 0, qubit 1. And so in the same way, our state here is TA food. It's never going to change the order. Our food can never eat the human is how we've phrased it here. And then we've also noted for our vertical ordering, there is a convention, or I guess there are 2 conventions that are commonly used for our qubit states, but we're going to teach the one that is used for the IBM quantum experience. If you ever see things that they're reversed a little bit, there are other conventions that people use, but they're mostly standardized in one of 2 ways. So if we want to go back to the actual mathematics, we want to create a tensor product for just 2 qubits, which most of the states we're working with are 2 qubit states. So if we say our qubit 0 is in state Q0, we can say that Q0 is equal to the 1 ket, or this 0, 1 vector, and qubit 1 is in state Q1 with a 0 ket, or the 1, 0 vector. We want to represent their combined state. So the way that we do that is with this tensor product, which we will define more explicitly on the next slide. So this is like where Qiskit diverges from, in fact, how I just wrote it. A lot of like textbooks and a lot of papers do write your qubit state as Q0, Q1, where your, I guess, like highest number qubit is, or your highest index qubit is on the rightmost side. If you're thinking of it in the computer science terms, if you're familiar with that, we'd say like our most significant qubit is rightmost, meanwhile our least significant qubit is leftmost. IBM, because they're kind of more computer sciencey, they put their most significant qubit, just call MSQ, on the leftmost side, and their least significant qubit on the rightmost side. So this makes sense if you if you're thinking of it from a computer science perspective, where if you remember our binary, we maybe have a state 1, 0. This guy is multiplied by 2 to the 0, and this guy is multiplied by 2 to the 1. So this is equal to 2. If we used the inverted indexing for this, which there are like historically, like there were computers that used the opposite arrangement for their bits. I believe it's called, it's really like, it's a really stupid name because it's from Gulliver's Travels, and it's like whether you think like the thin point of the egg is like the more important bit, or like the like thick bit of the egg. I forget the name of the convention, but it's this was actually like something that people went through in computer science. If you find it confusing, that's totally fair, because people do have opinions both ways. There were computers built um, that were like that are tended to go both ways. I'm gonna find the name for this. It's Big Indian or Little Indian. So the story in Gulliver's Travels was there was like a whole nation where one would break their boiled eggs at the big end, like the thicker end of the egg, and one would break their eggs at the little end, like the thin end of the egg. And they called themselves Little Indians. And it's like it was just like a big fight, and there was the same kind of big fight in computer science, and IBM and Intel used different conventions for Big Indian versus Little Indian, and now it's more standardized. I think Intel won, and IBM is not going to make the same mistake again, so they're hoping to like be in the right convention that gets adopted by the whole industry. So that's like a complete aside, but it is a really interesting thing from computer science history that you kind of see today in quantum computing, where a lot of physicists do use this convention, but computer scientists tend to use this convention. So we will always be using this one, like this is what we want to use here. And the notation, you can see here, this X with a circle around it is the tensor product. And on the next slide, we'll have the actual definition for this. I'm not going to write it out because I'm sure I will do it not. It's pretty straightforward. You take your 0th location of your first state, and your 0th location of your 0th state, and you multiply them, and that's your first row of your 2-qubit state. You then, for the second one, you take your 0th bit for your your 0th bit for your first qubit state, and then your first bit for your 0th qubit state, and you get your second row. And you do the same thing going all the way down. So I guess the way you'd write, like you can also write it, we don't have it written out on this slide, but this is 0, 0, 0, 1, 1, 0, 1, 1. It's the same kind of counting convention that we saw in binary. So you can see this is 0, 1, 2, 3. So if you ever forget which order it goes in, it goes in the same order that we've always counted in binary. We keep it consistent with that. And this is also the same ordering that we used for like that we used for Phil in Amon's dinner. So if we take Phil to be the 0th state and Amon to be the first state, or sorry, we take of qubit 1, and we take the pasta to be the 0th state and the pizza to be the first state of qubit 0, then we can kind of multiply them through and get the exact same kind of mathematics pictorially. And this state here, you can see this is the 0 state and this is the 1 state. And so this state over here is 0, 1. And it's written like this. And we can do that for all of the different 2-state options. So if you found that a bit confusing, you can instead think of it as multiplying your I guess 0th column or 0th row. I'll call it the first row of qubit 1 times the entire vector of qubit 0, and that creates your first 2 rows of your 2-qubit state vector, which you can see here. And then you can take your second row of qubit 1 and multiply it by the full qubit 0 state vector, and that gives you your 3rd and 4th rows, or your 2nd and 3rd rows, depending on how you're counting. So you can think of it either way, but it's pretty simple mathematics. I'd say like the tensor product is, if I was to not know what a matrix was, this is how I would multiply matrices, is just taking the tensor product. So if you were very confused when we originally did matrix multiplication, this kind of like just multiplying each element by the other element and getting all kind of permutations of this multiplication action. That's how tensor products work. And so you might find it a little bit more intuitive if you found that less intuitive. So now we want to go back to dinner, and we only had a two state options for Phil and Amon's dinner, but now we want to include dessert. So instead of just having, our, like, I guess we do still have a two-level system for both dinner and dessert, but now we functionally have a three bit system where 1 bit is our TAs, 1 bit is dinner, and 1 bit is dessert. So we can list out their dinner options, and I guess you may have already counted them up, but can anyone guess how many total options we're going to have for this, I guess, 3-bit system? Nice. Thank you, Tomas and Andrew and Drew and Xavier and Becruz and Mason and Anish. You guys are right on. So if you remember your kind of binary arithmetic, because we have two levels or 2 states for each of these, we're going to have our 2 as our base, and the number of options here is 1, 2, 3. So this goes 2 to the 3, which gives us 8. So yeah, that's and this is of course exactly the same for qubits and regular bits. Although again, the important thing with our qubits is of course the phase, which is not denoted in any way here. So you can write out our full set of options. We now have 4 possible Phil meals and 4 possible Amon meals. And we are still going to keep our ordering the same. So if we take this as our Q2, Q1, Q0, or TA, dinner, and dessert. So now if we want to extend our tensor products to 3 qubits rather than just the 2 we had before, we can perform the same action where we do the tensor product between 2 of the bits and then the results between the other 2 bits. I guess we should always go from left to right, or right to left, not left to right. We do it backwards from how we read. So we went here, and then we went here. And so you can see how this works out here, or I guess they went left to right. Does it matter? I don't think it commutes. I might be slightly backwards. But the result is just that you can perform the same operation with both of these levels, or both of these vector operations, these tensor product operations, and get now a 3 qubit state or a 3-bit state rather than just the 2-bit state that we had before. Okay. So this 3 qubit state makes it very obvious that it is a lot of mathematics to get to our final result, and this is going to become very tedious very quickly. So instead, we want to use a computer. We say NumPy, this means a computer, i.e. Python, to evaluate it for us. So we can evaluate these multi-qubit state vectors and then use the state vector simulator to make sure we're getting what we expect. So that is kind of the conceptual portion of this lab, and we're going to move to the quantum experience now. So get that set up, and send me any questions you have about this portion now, because I'm going to close out my slides and then I'm not going to be able to annotate as easily. So I'll give you guys like 10 seconds to do that, and then we'll move over. I'm not seeing any questions, so I'm going to stop sharing. Okay, cool. Actually, I see a raised hand from Tomas. Do you have a question? Maybe not. Oh, okay. Oh, why was it 0, 1, 0? This, I can't read. Oh, wait. Was it 0, 1, 0 our result? I think. I'm not totally sure. I'd have to. I cannot do tensor products very quickly in my head. We'll work through this in quantum experience, and then I will correct RTA if we have issues. Okay. And I also got a question from Kazi if state vector has errors in the quantum experience. State vector is only doing the pure mathematical form of this, so it's not even doing like a emulation of like a simulation. Like we're just doing the pure mathematics for it. So we're not going to get any errors at all. We're not going to get any effects of the finite number of runs of our system even. So our probabilities are going to be different from what we'd experience experimentally. Yeah, so with QASM, we will be able to see the, I guess, finite size of our system and the deviations from our ideal values, but we won't see any actual errors. It will only be due to like the finite number of runs that we're doing. Okay, so I'm going to share the quantum lab page. They did change the layout of this. So if it looks different, they just pushed an update to it literally today. So I'm sorry if like things are confusing because of that. We don't really have an easy way to fix it, or like we obviously can't revert their code or their cloud, but we will be posting up-to-date versions of what these what your simulator should look like as soon as we can. They just pushed it like the day at the lab. It does look cooler than it used to, I think. And it is all dark. One thing is like our text is like kind of ugly at the top, but cannot do much about that. Okay, so this week we're going to be like we're going to first import all the libraries we need. So make sure to run every step in the Jupyter notebook. Otherwise, you're going to get an error like, oh, you didn't import this function. I don't know what this function is. So that's all we're doing here, is we're just taking kind of the quantum circuit and simulation, like both functionality and backend from Qiskit, and then we're taking just the plot histogram version for the visualization, which gives you the probabilities for each state. And then we're importing NumPy, which we'll be using to evaluate these tensor products. So I'm going to run that. And what we're going to be using today is the NumPy function np.cron, or which is KRON, not CRON, which if you are familiar with like Linux-like machines, a cron job is just a job that auto starts whenever you turn on your machine. This is different. This is a short, this name is short for the Kronecker product. If you've heard, has anyone heard the name Kronecker before? Actually, commonly used distribution, not function, in mathematics. Nice. Thank you, Angela. Yeah, dead on. The Kronecker delta is a common like distribution, which is just kind of like a very sharp peak. There are, his name is also like in many things. I don't actually know all the things that you guys have that like you might have noted. So Jayden mentioned relativity. I definitely believe he was probably involved in everything. But definitely post any things that you are aware of that he was on. But yeah, so in this case, we're just doing the Kronecker product, which is the exact same thing as the tensor product. We just have a different name for it in NumPy. And we're going to use it to figure out the same tensor product we computed by hand, which is this 0, 1 times 1, 0 times 0, 1, or I guess 1, 0, 1 state. And you can see we have this, okay, in this case, we did do Q1 times Q0 and then Q2 times the Q1, Q0 results. So we did the opposite, where we did Q2 times Q1 and then Q2, Q1 times Q0 in the slides. I don't know, like I didn't write the slides, so I don't know why it was written that way. But we can just run it. And we can see even though the order of operations was different, we still got the same result. I don't believe this is generally true. I guess no, it should be generally true. I'm not 100% sure. Don't quote me on either way. But this is, regardless, this is the same state we managed to find by hand by just running through these states. And so now what I want you guys to do is this practice of finding instead the 0, 0, 1 state using NumPy. So if you are familiar with this, this is, I guess, I think it's this. No, I didn't like that. Okay. This is not using standard notation, but that is the state we're doing. And I want you to do the Kronecker delta or the Kronecker product operation for this 3-qubit state, and then send it in the chat. So thank you, Tomas, for your quick answer. I'll see if I can get one more person sending it out, and then I can show you how I would do this. Well, thank you, Xavier. Thanks. I think you guys are both right on with the result. Thank you, Mason. So I'm just going to copy this cell and make a new one with this modified state. So now instead, we want 1, 0, 1, 0, 0, 1. And then we can run the same thing. We've just changed what our state values are. And it's very quick to get this, this calculation done, and much quicker than doing it by hand. Thank you, Drew and Mason and Victor as well. Yeah, and this has no, tensor products are associative, so it doesn't matter which order we do it in. That's not the case for all operations. So do be mindful of what order you do things. Okay, so with that, we have our tensor products or our Kronecker products calculated. So we know what states we want to start with, and we can easily create our 2-qubit state vector for any state we want to create, or a 3-qubit n-qubit state vector, just using these Kronecker products. So now we're going to use the QASM simulator to visualize Bell states, which are 2-qubit states. And we're going to be using QASM as our backend. So to remind you of the difference again, the state vector simulator just kind of mathematically calculates the results. It pretty much performs the same like rotations on the blocks here on like a perfect state, and then it will give us the exact probabilities that are just the square of the amplitudes of our two states based off of this. On the other hand, the QASM simulator, rather than giving us the exact numerical probabilities, it will try to run the circuit on a computer that pretends to be a quantum computer, and it will get the results from that, and will get some deviation from the ideal behavior of our quantum state. So because it is functionally performing measurements on the circuit and just getting the results of our circuit many, many times, we need to add classical bits and measurements to our circuit. And then we can add artificial noise to our circuit output to make the simulation more realistic. There are like certain types of noise that we expect to see, like there's 1/f noise, which is like 1 over frequency. So as your frequency gets higher, your noise gets lower. There is like, I guess there's like different flux noise and thermal noise that you can get, and they all have their own kind of defined behaviors that you expect the noise to behave in. So you can define this thing called a power spectral density that defines how much noise power there is at any given frequency. And so we can then feed in that distribution, which depending on the distribution of your qubit frequencies, you can see how much that noise will impact it. So there are ways to artificially add noise, but it is optional and we won't be doing it right now. So in the lab last week, we created this phi plus state, which is one of the 4 Bell states. And this phi plus state is just these 0, 0, 1, 1 states. These entangled states can be defined or referred to by 2 parameters. We have this all kind of written out in case you want to review, but there is the parity and the phase. So the parity is if you multiply these 2 qubit states, 0 times 0, you get 0, or like you get an even number. You multiply 1 times 1, or sorry, not multiply, we add 0 and 0, you get 0, you add 1 and 1, you get 2. Both of these are even, so they're both the same. Whenever you add the same number to itself, like when you're in integers or in Z, then you will get an even parity. So it's just checking whether you have the same 2 states. If we had higher levels in our system, then this would still be the case with like a 2-2 state, but a 2-1 state would be different. So that's our parity value, is just what the 2 states for our 2 qubits are. So here you have our 0 and our 1, we add those, we get 1, which is an odd number. So that's an odd parity. And that's kind of the generalized definition of your parity. The other number is your phase, which is whether you have a plus or a minus between the two. So this is a 0 phase, and this is a pi phase. And it's just the relative phase between the 2 qubits. So it would also tell you whether like these would constructively or destructively interfere. So this is also like easy to kind of tell because it's denoted by the plus or the minus sign with the state definition. So now what we want to do, instead of creating our like phi plus state, we want to create our phi minus state. And so we want to, I'll kind of hide the answer. You guys may have already seen it, but we want to flip the sign of the 1, 1 part of the superposition without changing the 0, 0 part. So we don't want to change the value of our state. We just want to change the phase of our state. Does anyone know which gate is often called the phase gate? guys right on. Thank you, Surya and Kazi and Dennis and Dhruv and Mason and Austin and Jade. Um, and yeah, I think I missed some people. There's a lot, but you guys are all right on. It is the Z gate that we're using. So as a reminder, it rotates you around the Z axis of the block sphere. So it kind of keeps you in the plane, like the equatorial plane of your sphere. And that corresponds just the relative phase between your 0 and your 1 state. So what we're going to do to add this pi phase is do, instead of, we don't have to do an arbitrary phase operation, we'll just do the Z gate, which gives us a pi phase exactly. So to do this, we're going to start by just putting our 0th qubit in a superposition state. So that's what we're doing here. We're creating our circuit for our phi minus state. We are initializing a circuit with 2 quantum bits and then 2 classical bits. Then we're applying the Hadamard gate on qubit 0, and then we can draw that. And we can see what we get out. And you can see they fixed the printing for the classical bits since last week. This was really ugly last week, and now it's very clear to read. And all we've done is just initialize these 4, like 2 qubits and 2 classical bits, 4 total bits, and put a Hadamard gate on qubit 0. So now we want to add our relative phase for this state. So we're going to add a Z gate to qubit 0. And so all we're doing here is just adding that Z gate and then drawing the same circuit again. So you can see we just added a Z gate between these 2 plots. And then finally, I guess you guys probably already saw the hint or the answer. I guess you also have the notebook open, but we now need to actually entangle our 2 bits. And we all remember what our entangling gate is. In post if you do. Thank you, Tomas and Jade and Drew and Surya. Yeah, you guys are right on. It is the C0 gate, also called the CX in Qiskit, because again, the not operation is just going like between your 0 and your 1 state, which is an X rotation. You could also use a Y rotation, but then that goes through a different like phase path than we typically define it as, although our resulting location in the like XZ plane is the same. So we're going to use our controlled X gate or our controlled NOT gate with using qubit 0 as the control and qubit 1 as the target. And then we're going to add measurements where we put our, I guess it's like 0th qubit and our first qubit onto our 0th classical bit and our first classical bit. So these little like lists, this first thing is the qubits that we want to measure. And the second element are the classical bits where we want to store our quantum information that we've measured. So we can put a list of all the different qubits we want. We only have 2 in this case, but we're going to measure our 0th bit and our first bit, or our 0th qubit and our first qubit onto our 0th classical bit and our first classical bit. And we can run that and we get exactly what we generated here. So we can also, we could remove the measurement on the first qubit by just going to going to a single value for our quantum bit and our classical bit. So with this, oh, did I just add? Oh, we've already added this once. We've added the same operation again. So I'm going to run these again so we don't get, so every time you run these operations, so just to be, so I realize I've just like blazed over something that's very important. If you run these operations, you are making a modification to this element or this instance of your class. So we have a circuit here that we've added the CX gate to once already. When we run this cell again, we are performing the same cell operation again. So now we're going to, what I've done is I've just reinitialized our circuit without having this run. And now we get the same thing with just the 0th qubit measured. So I've gotten a really great question from Anantha Krishnan about whether we can reverse the operation of the X gate and the Hadamard gate. And so what I want you guys to do, this is, I love this question very much, actually. I want you guys to run like all these circuits again, but I want you to switch out your Hadamard gate for a Z gate and your Z gate for a Hadamard gate, and then run both these circuits. And I guess we haven't actually done the measurement yet. So we have done the measurement, we haven't gotten the result. Let me do the result first, so that we can then compare. But we will get to this question in just a second. I'm going to run through these, and I'm going to put this back to our 2 qubit / 2-bit measurement. And we're going to take our backend and then like execute our job with the number of shots we want, store the result of this job, and then get the counts and plot the histogram from the counts. The exact same as we did last week. You can see it's slightly different than what was run before because there's always some randomization. So now, as your task is to swap these gates like so. So this, instead of having the Hadamard or the Hadamard gate and the Z gate, we're going to have the Z gate and then the Hadamard gate. So what you should get is this. And then I want you to run the rest of the circuit and tell me whether you got the same results of this being 0, 0, and 1, 1. But we can also measure, we can use this to measure our phase written out here. And so we can see what we ended up with. I guess we probably should have done the phase first, but you can still just you can just swap the gates around and see what you get if you're ever unsure what a result should be. It's a really quick way to just kind of debug to make sure you're right on. Nice. Thank you, Tomas, for your numbers. Yeah, I think like you should get the same phase result, so or the same probability result, but you can also get the phase like we have here. This is our Hadamard then Z. And then this, so the Hadamard then Z direction, we get square root of 2, 0, 0, negative square root of 2. If we swap the two, so we have Z Hadamard, just like we said, we do get a different result of these two because so I guess I think that I'll open up the question if anyone can think why this didn't work, why we couldn't just do the Z first, because it is a really important nuance, and if there was, and it depends on our initialization for our states, and if we initialize to a different state, then this Z gate operation could totally work. Sorry for being like a little rambly. I think it is a very good question. Like if the gates commute, which sometimes they do, most times they don't. So yes, the order and the matrices do matter in this case. And Anantha Krishna is right on that Z time on the 0 ket gives you just the 0 ket. So if we're pointing up or down on the block sphere, we don't have any phase information stored on our qubit. It's all, I guess, like stored when we're along the equator. So when we do a Hadamard gate, we go onto the equator of our block sphere, and then we have like maximal ability to define the phase of our qubits. So in like a real quantum circuit, like a lot of times we're not exactly along our like polar axis. So maybe there could be more modification, but so that is why you do care about the phase that you are accumulating when you do go to these like polar, like 0 or 1 states. But whenever you want to do a phase operation, you are best off just doing it along the equator, or like after you've performed a Hadamard gate on one of these either 0 or 1 states. So Drew has asked a great question. What happens if we do 2 Hadamard gates? So what I want you guys to do is run 2 Hadamard gates and tell me what you get. I think it's easier to do it with a state vector simulator. I think I will ask a question about all the numbers that you guys gave me in just a second, but try running it with a state vector simulator and tell me what this matrix down here you get is. And I can give you the intuition for like what the actual meaning for this is as well, once you give me your numbers. But I got to make you guys work for it. Nice, thank you, Tomas. Got a little bit of a like, so I want to note in what Tomas sent. You can see there's like this -6 e to the -17. If you're confused as to why that's there, that's just a rounding error. Sometimes, like, or in general, like these, like Python has a finite number of bits it's using to represent these numbers. 10 to the -17 is obviously super teeny tiny, and we are using the state vector simulator, not the not a like probabilistic simulator. So there's no way we could get anything that has that small of a number when we're really only working with 0s and 1s and I guess like kind of common like 50-50 superpositions. We should never end up with such tiny numbers. So those are just rounding errors due to the programming language itself. It's nothing like you did nothing wrong. Python did nothing wrong. That's just kind of limitations of computers. So if we run that and see, I'll show you exactly what did on my screen as well. And you can see I also get a rounding error, but we ended up in the 0-0 state fully. So we wouldn't even need to do this. I guess we don't even need to do this entangling gate because our qubit 1 started out in the 0 state as well. But yeah, the Hadamard gate is like, if you run it again, you can kind of, I wish I could, if I had my iPad like shared on the screen, I could show you, but you can multiply it through. You can see that you just end up going like from pointing up to the equator, and then from the equator to back to pointing up. So that's how we end up with this result. The Hadamard gate, like Clark said, kind of it does reverse the previous Hadamard's operation. You can look at it mathematically and see how that works. So your Hadamard gate, I guess, is like 1 1 0 negative or 1 1 1 negative 1. And you can see if you multiply them, you end up with nothing. And so or you end up with like just like a kind of identity operation with the two. So you can, I'll leave that as an exercise to the reader to kind of prove that to yourself, that running a Hadamard twice gets you back to where you started. But yeah, so we successfully made the phi 9 state, and then we got distracted and made some other states, but they were pretty fun states too. And they all illustrate really important points on the block sphere. And I definitely like highly recommend you guys like continue thinking about these questions and asking these questions. Like, what happens if I put this state instead? Or what happens if I like use this gate? What if instead of doing a like pi phase on our qubit states, I did an RZ which is a z rotation of some arbitrary angle, and I only do it a 30-degree angle, or like a pi over 6 angle. What does that mean? What am I actually doing? What state do I get out? Definitely recommend doing stuff like that. I think RZ 0 and p dot pi over 6, which is what I just said. Maybe I can do that. Do I have that right? Oh, maybe I have the syntax wrong. I don't know the RZ syntax as well as I should, clearly. But I don't know where I went wrong. Angle qubit, thank you, Andrew. I always get it backwards. Great, now we're on our RZ with a pi over 6 rotation, and then we do our entangling operation. And now, if we do that, you can see we do have some, we still have the same total amplitude where it's 50-50, 0-0 state and 1-1 state. You can see there's still nothing on our 0-1 or our 1-0 state. We have just rotated the phase as we did before. And the result, though, is that we have this now like relative phase between our 0-0 and our 1-1 state that is like different from what we had before. Instead of it being a pi, this is a pi over 6 rotation. So it's pretty cool. You can create any state like that, and I'd recommend, like, these 2-qubit states are difficult to plot on the block sphere, but you could look at like the single qubit amplitude and see kind of where this phase is for a 1-qubit version of the state. Or like you don't even have to do this entanglement operation. You could just look at the 1-qubit state that we've created on qubit 0 and print that out. So just highly recommend doing that. It's a really easy way to like check your intuition, get the results, see if the results you get is what you thought you were going to get, and also like find new questions like, why did I get this result? And see if you can figure out yourself running it through mathematically or graphically with the block sphere, or ask on Piazza, why did I get this? I tried this thing. I don't get why this sequence of gates gave me this result. But it's like so nice being able to just check what something actually outputs very quickly with Qiskit. So to give you the overview for what we just did, we went through a process of designing a circuit to create the desired output state. In this case, the like phi minus Bell state. We started by looking at the features of the final state we wanted to generate. We decided which gates we needed to produce those features, so to create that phase. We then implemented that circuit with the gates to transform the initial state into the final state. And then we tested our circuit results through simulations. And then we went through a couple meanders along the way. So our key takeaways for this week is that you can use tensor products to create multi-qubit state vectors. The QASM simulator, which actually like emulates the behavior of a real quantum computer, requires classical bits and measurements in order to get the results, while the state vector simulator will just perform the mathematics we want. So if we were just going to check our hand-done math, we could easily do it with the state vector simulator. It would be faster. We can also use the QASM simulator to see what it's more likely to look like on a real quantum computer. And this is the gate sequence we want for the phi minus Bell state. We have some further reading on these states, and I'll start the post-lab Zoom feedback. You guys are, of course, free to go, but I'm going to go through the optional content using the Circuit Composer widget. So if you must go, I guess we're like already 5 minutes past, but if you must go, you can always go through this on your own time, but I hope it is helpful for those that want to stay. And this will also be recorded on YouTube if you do want to watch it later. So with this kind of update, we now, it was before this update, they added a Circuit Composer importable widget on Jupyter notebooks, which allows you to create circuits using drag and drop, and then generate your Qiskit code so that you can modify these circuits or do more complex operations you can't just drag and drop for. So we're going to import this circuit composer from their quantum widgets, and we're going to launch it. And what it does is it creates the exact same image as what you saw on the circuit composer we used previously. So you can just drag and drop a Hadamard gate or a NOT gate, or identity gate, or whatever we want on all of these. And we can perform measurements on them, going to our classical bits. We can do any kind of operation we want. So this RZ gate, in this case, we've had it as a pi over 2. I'm going to do a pi over 6 we had. Can easily add that. And then we can create a cell that will do the same thing as our QxQ code, or as our circuit we just created here. So this cell was just created by that. You can see it has our pi over 6 RZ. I could change this pi over 6 to be a pi over 12, and it would change the code dynamically. So this will create this exact same state in code. And then, because we have created it in code, we can then take the values of our the values of our circuit and simulate them in the back end. So I've done this over here I'll kind of recreate what I did earlier, where, let me delete these guys. I'll keep this guy. I created a C0, 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 and then so I've put all of my qubits in a superposition of 0 and 1 on all of them. And then I've done an entangling operation between qubit 0 and qubit 1, then on qubit 2 and qubit 1, and then on qubit 2 and qubit 0, and then I'll measure all 3. And this cell does that same output, and we've now saved this instruction set. And then I just wrote a really quick little simulation version that uses the QASM simulator to simulate this behavior. And you can see we get numbers around 0.125, which is what we'd expect for like an 8, like a pi, or yeah, like an 8th likelihood for each of these. These are all probabilities. I'd like to remind you, this is not the amplitude, this is the probability. So this is actually like 1/8 chance that we're in each of these states. And the states that we can be in are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So it's all the possible options. And that's kind of what I initially created. I think if I delete this guy, I don't recall. I think it does remain the same, because we've done, I guess, 2 entanglement operations on these. So if we instead start out in this state, we should get a 2-qubit entangled state with just 0, 0, 0, and 1, 1, 1. So you can see you can just play around with it and get either equal superpositions of all of our states, or like 3-qubit maximally entangled states, just by deleting a few gates and modifying it around. And you can really easily do it by dragging and dropping, and then running the simulations all in QxQ. Oh, and then Tomas has asked, why does it say pi instead of np.pi in the RZ gate? So I'll add one back in. You can see it says pi over 2 now. This is because when we imported NumPy, we didn't import like the pi function from NumPy such that we can use it directly. We just imported NumPy as NP. So whenever we want to access any functions in NumPy, we have to do np dot that function. We could do like, I guess up above here, if we did from NumPy import pi, we could instead do pi over 6, and it would still work. But if we didn't have this line, then we wouldn't have it defined like that. But it is just a matter of how we imported it. Yeah, you have to do this to write just pi rather than np.pi. Okay, cool. So with that, I think that's all of this kind of example, you can, like, there is more examples of like kind of pre-generated circuits. And we do have some extra reading with practice with tensor products down below, where it has kind of some more generalized and very mathematically heavy material. So I'm not going to go through it explicitly, but definitely ask any questions you want on Piazza. But it's a bit more advanced, and we don't totally need to go through it that explicitly. But yeah, are there any questions at this point? So Elon has noted you can also write import star from NumPy to write pi instead of np.pi. This is true, but then you are importing all of the functions in NumPy into your namespace, so you can have collisions with function names. So it's generally, like, people consider it bad practice to do import star. I still do it because I am lazy and I like to be able to type less. But it can be dangerous if you don't know what all functions exist in some of these libraries. What if we still wrote it as np.pi? Does it cause an error? So in this case, we have also, and you can see they did actually the same thing down here. So because we imported it as at the very top, we imported import numpy as np, we actually have two import statements. If we did not have this import statement, we would have only gone through, like, we would only have the pi function imported. So we wouldn't be able to use any functions from numpy other than pi. So yes, like np.pi would cause an error if we hadn't run this line as well, but this line imports every single function in NumPy under the np namespace. So it wouldn't cause an error in this case. But if we only had that single pi function imported, then it would cause an error. Okay, cool. All right, do we have any final questions? Okay, well, if not, I hope you all have a wonderful week. Definitely post any questions that arise on Piazza. Let us know. And definitely play around with Qiskit. There's no reason not to play around with it and run any circuits your heart desires. You can always see what you like, any result that you want to create. Or you can even, like, try to, if you want to create a certain state and you're not totally sure how to, you could post in Piazza, like, can you lead me down the right direction, the right steps to create like this more complicated 4-qubit state? Okay, thank you, everyone. Hope you have a wonderful week and a wonderful evening. And I hope that you got something out of our Qiskit overview today. Bye, everyone.